Hey guys, Mr. Smith here. We're back for another video lesson. In this lesson, we're going to review how to calculate frictional forces and do another example with a system with multiple objects, but this time it'll have 3 objects. I don't believe this video will take as long as the previous one, which is about 45 minutes long, hoping more for about half an hour. We'll see. No promises, so don't get mad. Let's get started. So you guys learned about frictional forces in your grade 11 course. So, I'm not going to go too far back in deriving everything. But if you think about what happens when you pull or push like anything across a countertop. So imagine like a case of bottled water, because those things are pretty heavy. Like initially, like if you push a little bit, like it's not going to move, right? Just if you apply the tiniest bit of force, it's not going to move. So you're applying a force one way, but it's not moving. So there must be some kind of static friction force opposing the motion, right? But that static friction force isn't fixed, because if I push harder, the case still is not going to move. If I push harder, well, that static friction force must get bigger too if the box isn't going to go anywhere. And eventually you push hard enough so the box starts to move. And once the box starts to move, we still have friction, but we have this kinetic friction force that is applied to the box. So you hopefully saw some kind of diagram like this in your grade 11 course, where just as we discussed, so this Fs is the force of static friction, and this is the applied force. So basically you push, and you're pushing and pushing, and the object's not moving. You push harder and harder and harder. And the harder you push, the larger this static force of friction gets, labeled Fs in the diagram. You push and push and push and push and push, and eventually you push hard enough that it starts to move. And when it starts to move, that highest static friction force you get, we call like the maximum static friction force, or Fx comma max. Once it starts to move, what you guys hopefully saw in your grade 11 course is that you still have a friction force, but in most situations, that friction force while it's moving is less than the maximum static friction force. We call that the force of kinetic friction. I'll just move my image up here for now. And just quickly talking a bit more about that. So the greater the mass of an object, so obviously the more mass, the larger the force of gravity. And if your object isn't accelerating into the table or magically flying off the table, then that contact force, the normal force, has to balance your weight, the gravitational force. And so the larger the mass, the larger the normal force. And the larger the normal force, the greater the applied force you need to keep that object moving. So if the mass is small, you got a small normal force, and you don't need a large applied force to overcome kinetic friction. But if you have a larger mass, like it doubles, so does the normal force and the applied force as well. Big ideas is that static friction and kinetic friction, kind of two different things. Most of the time, the force of kinetic friction is a bit less than the maximum static friction. So this corresponds to that maximum applied force you need to make the object begin to move. What are the equations governing friction? So you guys would have learned, different surfaces have different coefficients of friction. And surfaces have a coefficient of static friction and a coefficient of kinetic friction. So two different coefficients depending on if it's moving or not moving. The reasons why they're different, hopefully maybe you investigated that during your in your grade 11 course. But again, this is actually, these coefficients are determined experimentally. And so maybe in grade 11 you were given just a huge list of different coefficients of friction. If they're needed, they'll be given to you in a question. but you could go look up some engineering guide online and see coefficients of friction for all kinds of stuff. That's how you calculate these two coefficients of friction. Now, for our purposes, we're going to be interested in calculating forces of friction. So if we rearrange those, the force of static friction max, just multiplying up the Fn, is this mu, this coefficient of static friction, times the normal force. And if we rearrange this guy, the kinetic friction force is equal to mu k times Fn. So, what I'll tell you guys, most of the time, for our purposes, we might just use force of friction equals mu times Fn, because the situation will be really obvious whether the object is stationary or whether it's moving. So this is the big idea. Force of friction is this coefficient of friction. That's the Greek letter mu, so not like mu from Pokemon, mu. And you get it by multiplying by the magnitude of the normal force. But in reality, there are two different forces of friction, one for when it's not moving, one for when it's moving. In our first example, we're going to hit on that. And then as we move throughout the course and we look at different problems, you guys won't have to worry about, am I looking for the coefficient of static friction or kinetic friction? I'll just give you, hey, here's the coefficient of friction, FF equals mu times Fn. So let's look at our first example here. So we have a crate of fish resting on the floor of a delivery truck, and we've got the coefficients of friction, static and kinetic. So you can see the coefficient of static friction a little bit more than the coefficient of kinetic friction. That is usually the case. I think there are some substances where they're equal or swapped, but not many. We're going to use 9.80 for meters per second squared. So I'll be good here, and we'll have our answers to 3 sig figs as well. So what are the force of friction and the acceleration? So A, if a horizontal force of 75 newtons is applied, and B, if a horizontal force of 95 newtons is applied. So first of all, let's look at the, let's just draw a little free body diagram going on here. So we have our crate of fish. Obviously, gravity acting down, and normal force acting up. And we, let's see. So let's say I'll say we're gonna push this way. So I'm gonna let our acceleration be to the right here. And if I'm pushing this way, I have my, I'm just gonna call this FAP, and that's gonna change from parts A and B. So force applied, and then we would have a friction force acting backwards. I'll label it FF for now. So depending on whether we have a large enough force, that might be static friction, that might be kinetic friction. But let's look at part A. And first, let's analyze the y direction. So in the y direction, sum of forces in the y direction equals the mass times acceleration in the y direction. But of course, it's not accelerating in the y direction. This is equal to 0. So this is our classic Fn minus mg equals 0. So the normal force actually equals the force of gravity, mg, and we can actually calculate that. And that's not going to change for the whole problem. So we can use, so 18 times 9.8, or 18.0 times 9.80. 18 times 9.8. Got it. So we'll use 176 for the normal force throughout this problem. So we have to consider, is that horizontal force enough to actually get that crate to move? So let's look at what's the maximum static friction force? And we talked about earlier, that's equal to mu s times Fn. which we now know. So mu s, that's 0.45. Fn, 176. So if we calculate that, 0.45 times 176, we get 79.2. So if we think about this, the maximum static friction force is 79.2. In part A, we're only applying a force of 75 newtons. So what this is saying is we're not applying a force big enough to even get this crate to move. So for A, since F_app, which equals 75 newtons, is less than that maximum static friction force, the crate won't move. So the in this part A here, our object's not going to move. It's that force. It's not even relevant. The applied force is going to be 75 newtons, and the force of friction will also be 75 newtons. That force of static friction will be 75 newtons. It's not near its max, so it's not going to move. You'd have to push with a 79.2 Newton force in order to get it to move. So part A won't move. Part B, we can see, well, now we figured out that maximum static force. So now we know if we apply a 95 Newton force, it is going to move, and that force of friction is going to be the force of kinetic friction. So do I have a second slide? I do not. So what I'm going to do, since you guys have this written down, and because it's a video that you can just come back and look at these figures, I can just erase these. Shouldn't be a big deal. There's a way to erase these a bit more quicker. But all right, so we did A. Let's talk about B. So part B, we now know it's going to move. And so now for part B, let's look at the Newton's second law in the x direction here. So the sum of forces in the x direction equals mass times acceleration in the x direction. Well, I should have said, what are the force of friction and acceleration for part A? So for part A, the force of static friction, or what we called FF, equals F_app, which was 75 newtons, and the acceleration was 0 meters per second squared. So I believe I did talk about that, but we didn't actually write it down. So for B, we have the force of friction, and in B, we know it's moving, we know it's kinetic friction. And we have the, I have my x direction to the right as positive. So I'll say F_app minus FF equals MAX. And in this case, so the question asks for the force of friction and the acceleration. So there's two ways you could do it. So if you prefer, so you could write F_app minus mu k times Fn equals MAX, and then you could, in this case, we know UK, we know Fn, we know we know M, and we know F_app. So you could solve for the acceleration, and then you have to go back and plug in for FF. What some people like to do is, once they have the normal force, they like to just calculate the force of friction right away. So that's fine. I think I'll do that here, actually. So kinetic friction is 0.41. So the, I said kinematic. It should be kinetic. So the kinetic force of friction here, let's just calculate ahead of time since the question wants that. Kinetic, 0.41 times 176. I got 72.2 newtons. So a little bit less than that maximum force of static friction. And so I might erase this last step here. And then now we just know Fn directly. But sometimes, some people might prefer just to leave it in a more general sense. And I might do that for some questions too. Yeah, but let's finish this off, guys. So we got the kinetic friction force done, 72.2 newtons for part B anyway. And the applied force, or excuse me, we're finding acceleration. The acceleration would be the applied force minus that friction force we calculated divided by the mass. So we have 75 minus 72.2, all divided by, it's 95 Newton force. Please forgive me. And divided by the mass, which was 18 kilograms. So 95 minus 72.2 divided by 18. So about 1.27 meters per second squared. All right, so not an overly crazy complex problem, but it did touch on the difference between static friction, kinetic friction. So before we even did part A, we found the maximum force of static friction and saw that our horizontal force wasn't enough to make it move. And so that the horizontal force, applied force, had to balance exactly the force of friction, so 75 newtons. Once we knew in part B that our force was large enough to make it move, we knew that FF was a kinetic friction force. We could calculate it, and then we solve for AX. So in the future, so that was an example where we tied in both. I can tell you guys, in the future, when we do problems, it'll be obvious whether it's moving or not moving. And we will just calculate our force of friction by using mu Fn. And, if it's really obvious that a object is moving, I won't say it's the coefficient of kinetic friction here. I'll just say the coefficient of friction, and you can trust that you're given the appropriate one for whatever you do. All right, so we did an example with friction. We're now going to do an example with 3 different objects instead of 2, tying in pulleys. So just kind of ramping things up and broadening our horizons a bit. So in this question, when I do this question with my students, I usually on the fly just make up masses for Papa Smurf, Brainy Smurf, and Smurfette. And so we're going to do that too. So let's just say that Brainy Smurf is, I don't know what a good mass for a Smurf is. They're kind of small. So let's say 4 kilograms. Let's say Papa is, he's had too many Smurf beers over the years, so 7 kilograms. And Smurfette, we'll say, maybe is a little bit lighter than Brainy Smurf. What we're going to do is we're going to find the acceleration of this system. So I think we could all kind of see, since Smurfette weighs a lot less than Brainy and Papa combined, that Brainy Smurf is going to be accelerating down with some acceleration. Papa Smurf will be accelerating down with that same acceleration, but like the coin problem we did in our last lesson, Smurfette is going to be accelerating up. So in this problem, we're going to set up free body diagrams for all 3. We're going to apply Newton's second law for all 3, keeping things in general terms. And then I'm going to show you guys how we can take that system of equations and find a general value for the acceleration of the system. And then we'll plug in our masses and we'll see what we get. So to start off, let's do free body diagrams for each of the Smurfs. Switch to yellow here. And actually, let's decide on, I think we'll call them, instead of like MB, MP, and MS. Actually, let's just do that. Say that's Brainy, Papa, and Smurfette. All right, that should be good. So let's do a free body diagram for each one. And I'll start with Brainy, I think. Get back to yellow here. So what's going on with Brainy Smurf? Well, obviously, his weight, gravity pulling him down. Now, what's interesting with Brainy Smurf is he actually has two tension forces because there's a rope connecting him to Smurfette and a rope connecting him to Papa Smurf, and they're not necessarily going to have the same tension. So I'm just going to call this FT1, and I'll call this second tension FT2. You could call them whatever you want. Like maybe you'd like to call them like capital T for tension, and then the tension between Brainy Smurf and Smurfette, and the other tension could be the tension between Brainy Smurf and Papa Smurf. Like that's fine too. Later on, we use T for something different. We use it for period for some uniform circular motion. Some might just use FT1, FT2 in this case. And for Brainy, we know that he'll be accelerating down. So I'm going to choose down as positive. So that's for Brainy Smurf. What about for Papa Smurf? So Papa Smurf has his weight, ms times g, going down. And Papa Smurf only has the one rope attached to him, and it's that rope that we assigned tension FT2. And Papa Smurf is accelerating down as well. Oh, that's Papa Smurf. So that should be MP for sure. You'll have to forgive me. MP. And finally, we have Smurfette. Smurfette has weight going down, and she has a tension pulling her up. That was the one we called FT1. And Smurfette will be accelerating up, so we'll choose up to be positive for her. So step one, again, draw the free body diagrams, choose a direction to be positive, and it makes a lot of sense, and you should choose that direction to be the direction of the system acceleration. So A. And that value for A is going to be the same for all of the Smurfs. So let's look at Newton's second law for Papa Smurf and Smurfette next. Now, I think I have enough space. I'm just going to do it on the screen here. So for Papa Smurf, so we have sum of forces. And there's only one direction here. So if you want to do, I'm just going to leave it as sum of forces equals the mass of Papa Smurf times the system acceleration. And careful with our sign convention here. We chose down to be positive. So it's gravity mpg in the positive direction, subtract ft2, and that equals mpa. So thinking about things we don't know ft2, and we don't know A. That's two things we don't know. And let's look at Smurfette as well. I'm going to leave a bit of space. So for Smurfette, we have sum of forces equals mass of Smurfette times A. And for Smurfette, we have up being positive, so that we'll have FT1 in the positive direction. We're subtracting the force of gravity, ms times g, and that equals msa. So notice, I might just call that 1 for now. I'll call this equation 2 for now. In Papa Smurf's equation, one equation, two unknowns. In Smurfette's, same thing, one equation, two unknowns, don't know the tension, don't know A. But like this is a different tension. So right now we have two equations and three things that we don't know. Now, I know that this question just wanted the acceleration, but in other times it might be useful to find the tensions too. So right now, two equations, three unknowns. Let's go to, let's set up Newton's second law for Brainy Smurf, and then talk about how we can solve this system of three equations with three unknowns. And we might use substitution this time. So for Brainy Smurf, sum of forces equals mass of Brainy times acceleration. So let's just refer to our free body diagrams. So for Brainy, in the positive direction, we have his weight and FT2. We have mass of Brainy times G plus FT2 going in the positive direction. And we have FT1 going in the negative direction. Equals MBA. And I can call that equation 3 for now. This is the third equation, and it has 3 things we don't know: FT1, FT2, and the system acceleration. And our goal is to find the system acceleration. So how do we solve 3 equations, 3 unknowns? In your grade 10 course, you really did 2 equations, 2 unknowns, but it's actually not too bad. We're going to use substitution. And so in questions like these involving pulleys, generally, it's never a bad idea to actually get an expression for the tension. So I'm going to solve this first equation for Papa Smurf. I'm just going to rearrange it for FT2. So if I bring FT2 to the right, it becomes positive, and then I'll be left with MPG, and I'll have to subtract MPA. So I've got an equation for the tension 2. And I can do the same thing. I can isolate FT1. FT1 equals MS, move the MSG over, it'll be positive, plus MSA. And now we can use substitution, because check this out. If I plug this tension force into Brainy's equation, I'll just have A left. And if I plug in Smurfette's for the other tension, that's just A as well. And so look what happens as we sub those in to our equation here. So I'm going to just make a little note that we're going to sub 1 and 2 into 3. So we're going to use that method of substitution you guys learned in your grade 10 math course. So we have MBG plus, what is FT2 equal to? Well, we said FT2 is MPG minus MPA. And minus brackets. So careful with, we're plugging in FT1, which is a binomial. So we should maybe put it in brackets so you don't have any sign errors. And we said FT1 is MSG plus MSA. And that equals MBA. So guys, if you look at this equation, we know all the masses, and we obviously know G. The one thing we don't know is A. And there are different instances of A in that equation, but we can use factoring like terms, so we can isolate that. So that's what we're going to do now. So at this point, it's just a bit of collecting like terms, a bit of factoring. So you can, if you're comfortable, probably shave off a step or 2. But I'm going to show a few steps. So I'm going to drop the brackets. So this would be minus MSG. So remember, it's minus MSG, and we'll be subtracting MSA. Equals MBA. I want to get all the acceleration stuff on one side. So I'm going to move all the things involving acceleration to the right. And then note that the remaining terms, I'll have a G in them. So it might save some writing and also just maybe save some calculations, just to common factor out the G. Also just looks nicer. Plus, I'm usually a math teacher, so yay, factoring, rawr. MB plus MP minus MS. And on the right, so we're going to have all A terms, and we'll be able to remove an A from each of them. And so we'll have MB. This term here for Papa Smurf, we'll move it over, will be positive MP times A. And then same thing here, this minus MSA, move it over, becomes positive, we'll have plus MS. And if we divide everything by MB plus MP plus MS, we get this cool, tidy equation for the system acceleration in terms of G and their 3 masses. And now we're ready to plug in. So we could have definitely plugged in those masses earlier, but I like having things in terms of in a general sense, because then we can play around with the problem afterwards. Like, for example, we could find what mass for a Smurfette would be required to maybe reduce the acceleration down to a certain value or even 0. So we have 9.8. Mass of Brainy was 4 plus 7 minus 3, I think we said, over 4 plus 7 plus 3. And we'll have our value for the acceleration. 9.8 times, that would be 8 divided by 14. So with these masses, this system of Smurfs would accelerate at 5.6 meters per second squared. So in that example, not really anything new, just maybe a more complex system than you're used to analyzing. I've given you a strategy for handling when there's 3 equations and 3 unknowns involving tensions. Often you can isolate the tensions, like we did here, and use substitution. So that can be helpful. And we've solved this problem in a general sense and then plugged in. So I know for my summer school course right now, you guys are going to be doing the little elves problem. And the problem we did right here will be helpful for you to refer to as you set that problem up. And if you're watching this video and you're taking this course with me at a later time, you likely will be doing the elf problem too. What's next? In our next lesson, we're going to talk about inclined planes. So we're going to add just that one complication in there. We're going to look at planes with friction and without friction. And that's almost going to wrap up our discussion of motion and dynamics in 2D for now. That's what's down the pipe. Hope you guys are staying well. Hope you guys have a good day. We'll see